Hi, my name's Mark Sanderson, and I'm going to describe some work that I did jointly with Nicola Ferro from the University of Padova. What have we done? We've compared a recently published ANOVA significance test to a classic significance test, the t-test. What we find is that the ANOVA test looks promising, but it might be a little too sensitive as it's currently set up. More worryingly, our paper also shows that there is some evidence that classic tests like the t-test are also potentially too sensitive, which might be leading to some issues of publication bias in our community. If you want to download our paper, the URL is down here. What do we use significance for? Well, when we're comparing systems, say system A against the baseline B, we want to understand whether A is better than B. We perhaps run that system on an offline test collection. That test collection maybe has 50 topics. We run the system against each of those topics, so 50 dots along this graph, and we compare A to B. We get a score that A is perhaps better than our baseline, and we want to know whether that's a real difference. So what we do is we often run things like a paired test. Because the systems behave similarly across the topics, we pair up those topics and then we aggregate comparisons across those topics. Classic test collections that we use include the SIGN, the Wilcoxon, and the t-test. Those tests have been around for decades, but recently there have been some publications, this one in 2017 and a more recent one by me and Nicola in 2019 that use an ANOVA approach for significance testing. The approach that both these papers describe is that they split the document collection in a test collection up into pieces, and they repeat tests on each of those pieces. As interesting as these two papers are, neither of them have really done an extensive comparison between their ANOVA tests and these classic tests, and that's what we do here. So how do you decide whether one significance test is better than another? Well, one approach is to use a topic splitting methodology. So if you have a test collection with 50 topics, you could randomly partition it into two equally sized pieces. And then you could take your test of A against B, run it on one topic set, then run it on another topic set, and then compare the conclusions that you get. If you find that both topic sets tell you that A is better than B significantly, that's good. If you find, for example, that the opposite happens on each topic set, that's bad. And then there are other kind of contingencies with combinations of significance and directionality. What you might do is then run those comparisons across multiple different runs. So maybe you've got runs A through to G, and you compare them for both significance and directionality. So we find that B is significantly better than D, F is significantly better than A or B. But on the other topic set, we find that A is not significantly, the F is not significantly better than A, but A is more better than F. With the other two tests, we find that they are the same. If we had this kind of situation where two comparisons turn out to be the same, but one turns out to go in the opposite direction, we would count that as two AAs and one AD. So in our experiments, what we do is we run tests on an unpaired t-test, a paired t-test, and the ANOVA test that Nicola and I published last year. And then we run this all on this data set, which has a large number of topics, a great many runs, and about 500,000 documents. Let's look at some results. So the first table we see is for the AA measure, consistent, significant measures across two topic sets. We see the results for the ANOVA test as well as the paired and the unpaired test. And what we see is that AA is much larger for ANOVA than it is for the paired or unpaired test. You notice these aren't integers. That's because we repeat the experiments 100 times and then take the mean. The gap between ANOVA and the paired test is particularly big when we're looking at topic set sizes that are small. For example, 5 topics. It's a little bit extreme, but if you had a very small test collection, the ANOVA test is very good at finding these consistent, significant differences. Unfortunately, when we go look at the AD, we find that ANOVA isn't as good as perhaps we might have hoped. The paired and the unpaired tests run very well. They don't find any inconsistent significant measures across the two topic sets. But for ANOVA, there are a notable number of these AD measures. Now, this is about 5 or 6 in this case out of 5,000 comparisons, but that's still more ADs than you would really like to see in a significance test, particularly given that a perfectly serviceable test like the t-test gets you 0 ADs. We then looked at these 4 measures, AA, AD, MA, and MD together. Why did we do that? Well, It's because these four measures are all measures that might cause you to think to publish a paper. If you find that A, your system is better than the baseline and it's significantly better, you might be liable to publish your work. And the question is that significance something that's actually real, or is it just something that happened by chance? Well, when you're looking at this measure of agreement across the two topic sets, the only one that is consistent are the AA measures. The other three, well, actually, if you tried it on the other topic set, you would have not got agreement. So, Wisdom wants significant advances. All of the conferences ask us to demonstrate significance. So if we get significance, we are encouraged to publish. So what we did is we used this measure bias. The details are in the paper, where we measured the fraction of measures that are not agreeing across the two topic sets as a fraction of the measures that do agree across the two topic sets. Here, we were struck to see that the t-test is actually worse than the ANOVA test. It's because of these MA and MD measures being quite large here, and ANOVA finding a lot of AAs. But it's striking that ANOVA, when it comes down to the bias measure, is actually a little bit better. The other kind of testing we did was to broaden the way that we examine these tests. Typically, when people write papers trying to help you decide which significance test to use, they use a wide range of runs from a large number of participants. Typically, they draw runs from a TREC track. But that's not the reality of how most people do their experiments. Most people have one system and some variants of that system, system A in version 1, 2, or 3. So what we did is we went back to our runs and just identified those from individual participant groups. We're going to show you a couple of tables here, one from the group FUB and one from the University of Glasgow. So when we look at the AA tables, we see a kind of a similar picture to what we saw earlier, ANOVA getting more AAs than the paired and unpaired test. When we look at AD, we find that ANOVA is doing even worse than it was when we were testing on the large number of runs. So we see a measure here, say, for ANOVA on the University of Glasgow runs, where it's getting 2 ADs. And this is over a small number of runs and about 40 comparisons. So you're getting 2 ADs out of about 40 comparisons. That's really just too many inconsistent, significant decisions that the test is making. And that really tells us that ANOVA is not yet ready for use by researchers. We then reran this bias measure, and this was the part that really surprised us, because what we found was that really both the ANOVA test and the paired t-test have a large number of potentially biased decisions that they identify. In fact, the paired t-test finds more biased decisions than the ANOVA test. The University of Glasgow is a particularly interesting one because the Glasgow runs are actually quite similar to each other. And when runs are very close to each other, it's quite difficult for significance tests to separate those accurately. And we see that with both the paired test and the ANOVA test. The ANOVA test is much more willing to find significance than the paired test, but when the paired t-test finds significance, it's in these potentially biased situations. Okay, so the conclusions of our work are that we tested this new ANOVA model extensively against the paired t-test, and we found that the ANOVA model, when tested in those kind of standard large participant run situations, it actually performs quite well compared to the t-test. However, when we try it on participant-only runs, the runs from just one research group, we find that the ANOVA model is notably over-enthusiastic about finding significance, and that leads to lots of inconsistent results. So, you might say, okay, well, I'm going to stick using the t-test then. Well, the final bit that I showed you was that the t-test is also potentially not as reliable as we perhaps thought it was. And this does cause myself and Nicola to worry that there is the potential for publication bias in our community. I want to emphasize that we didn't show publication bias, we showed the potential for publication bias, but we do think that more work is needed. So thank you very much for listening. This work was supported by a research grant in Australia, and Nicola Ferro was supported by his university in coming over to visit me in Melbourne.